Climate change from Wikipedia, the free encyclopedia, at en.wikipedia.org. The text of this recording is current as of the 30th of October 2021. This article contains the following sections: 1. Terminology. 2. Observed temperature rise. 3. Drivers of recent temperature rise. 4. Future warming and the carbon budget. 5. Impacts. 6. Responses, mitigation and adaptation. 7. Policies and politics. 8. Scientific consensus and society. And 9. Discovery. Contemporary climate change includes both global warming caused by humans and its impacts on Earth's weather patterns. There have been previous periods of climate change, but the current changes are more rapid than any known events in Earth's history. The main cause is the emission of greenhouse gases, mostly carbon dioxide, CO2, and methane. Burning fossil fuels for energy use creates most of these emissions. Agriculture, steel making, cement production, and forest loss are also significant sources. Temperature rise is affected by climate feedbacks as well, such as the loss of sunlight reflecting snow cover and the release of carbon dioxide from drought-stricken forests. Collectively, these amplify global warming. There's a map: average surface air temperatures from 2011 to 2020 compared to the 1951 to 1980 average. There's also a graph: observed global average temperature change since the pre-industrial era. The main driver for increased global temperatures in the industrial era is human activity. Natural forces add relatively minor variability. There's then one last graph: CO2 concentrations over the last 800,000 years as measured from ice cores, blue and green, and directly, black. On land, temperatures have risen about twice as fast as the global average. Deserts are expanding, while heat waves and wildfires are becoming more common. Increased warming in the Arctic has contributed to melting permafrost, glacial retreat, and sea ice loss. Higher temperatures are also causing more intense storms and other weather extremes. In places such as coral reefs, mountains, and the Arctic, many species are forced to relocate or become extinct as their environment changes. Climate change threatens people with food and water scarcity, increased flooding, extreme heat, more disease, and economic loss. It can also drive human migration. The World Health Organization is calling climate change the greatest threat to global health in the 21st century. Even if efforts to minimize future warming are successful, some effects will continue for centuries. These include sea level rise, as well as warmer and more acidic oceans. Many of these impacts are already felt at the current level of warming, which is about 1.2 degrees Celsius, or 2.2 degrees Fahrenheit. The Intergovernmental Panel on Climate Change, IPCC, has projected significant increases in these impacts as warming continues to 1.5 degrees Celsius, 2.7 degrees Fahrenheit, and beyond. Additional warming increases the risk of triggering critical thresholds called tipping points. Responding to these impacts involves both mitigation and adaptation. Mitigation, limiting climate change, consists of reducing greenhouse gas emissions and removing them from the atmosphere. Methods to achieve this include the development and deployment of low-carbon energy sources such as wind and solar, a phase-out of coal, enhanced energy efficiency, and forest preservation. Adaptation consists of adjusting to actual or expected climate, such as through improved coastline protection, better disaster management, and the development of more resistant crops. Adaptation alone cannot avert the risk of severe, widespread, and irreversible impacts. Under the 2015 Paris Agreement, nations collectively agreed to keep warming well under 2 degrees Celsius through mitigation efforts. However, with pledges made under the agreement, global warming would still reach about 2.7 degrees Celsius by the end of the century. Limiting warming to 1.5 degrees Celsius would require halving emissions by 2030 and achieving net zero emissions by 2050. Section 1. Terminology. There's a diagram. Climate change is driven by rising greenhouse gas levels in the atmosphere. This strengthens the greenhouse effect, which traps heat in Earth's climate system. Before the 1980s, it was unclear whether warming by greenhouse gases would dominate aerosol-induced cooling. Scientists then often used the term inadvertent climate modification to refer to the human impact on the climate. In the 1980s, the terms global warming and climate change were popularized. The former refers only to increased surface warming. The latter describes the full effect of greenhouse gases on the climate. Global warming became the most popular term after NASA climate scientist James Hansen used it in his 1988 testimony in the US Senate. In the 2000s, the term climate change increased in popularity. Global warming usually refers to human-induced warming of the Earth system, whereas climate change can refer to natural as well as anthropogenic change. The two terms are often used interchangeably. Various scientists, politicians, and media figures have adopted the terms climate crisis or climate emergency to talk about climate change, and global heating instead of global warming. The policy editor-in-chief of The Guardian said they included this language in their editorial guidelines to ensure that we are being scientifically precise while also communicating clearly with readers on this very important issue. Oxford Dictionary chose climate emergency as its word of the year in 2019. It defines the term as a situation in which urgent action is required to reduce or halt climate change and avoid potentially irreversible environmental damage resulting from it. Section 2. Observed temperature rise. Main articles: Temperature record of the last 2,000 years and Instrumental temperature record. There's a graph. Global surface temperature reconstruction over the last 2,000 years using proxy data from tree rings, corals and ice cores in blue. Directly observed data is in red. There's then another graph. Land surface temperatures have increased faster than ocean temperatures. Multiple independent instrumental datasets show that the climate system is warming. The 2011 to 2020 decade warmed 1.09 degrees Celsius, between 0.95 and 1.20 degrees Celsius, compared to the pre-industrial baseline, 1850 to 1900. Surface temperatures are rising by about 0.2 degrees Celsius per decade, with 2020 reaching a temperature of 1.2 degrees Celsius above pre-industrial. Since 1950, the number of cold days and nights has decreased, and the number of warm days and nights has increased. There was little net warming between the 18th century and the mid-19th century. Climate information for that period comes from climate proxies, such as trees and ice cores. They show that natural variations offset the early effects of the Industrial Revolution. Thermometer records began to provide global coverage around 1850. Historical patterns of warming and cooling, like the medieval climate anomaly and the Little Ice Age, did not occur at the same time across different regions. Temperatures may have reached as high as those of the late 20th century in a limited set of regions. There have been prehistorical episodes of global warming, such as the Paleocene-Eocene thermal maximum. However, the modern observed rise in temperature and CO2 concentrations has been so rapid that even abrupt geophysical events in Earth's history do not approach current rates. Evidence of warming from air temperature measurements are reinforced with a wide range of other observations. There has been an increase in the frequency and intensity of heavy precipitation, melting of snow and land ice, and increased atmospheric humidity. Flora and fauna are also behaving in a manner consistent with warming. For instance, plants are flowering earlier in spring. Another key indicator is the cooling of the upper atmosphere, which demonstrates that greenhouse gases are trapping heat near the Earth's surface and preventing it from radiating into space. Regions warm at various rates. The pattern is independent of where greenhouse gases are emitted, because the gases persist long enough to diffuse across the planet. Since the pre-industrial period, global average land temperatures have increased almost twice as fast as global average surface temperatures. This is because of the larger heat capacity of oceans, and because oceans lose more heat by evaporation. Over 90% of the extra energy in the climate system over the last 50 years has been stored in the ocean. The rest has heated the atmosphere, melted ice, and warmed the continents. The northern hemisphere and the North Pole have warmed much faster than the South Pole and southern hemisphere. The northern hemisphere not only has much more land, but also more seasonal snow cover and sea ice. As these surfaces flip from reflecting a lot of light to being dark after the ice has melted, they start absorbing more heat. Local black carbon deposits on snow and ice also contribute to Arctic warming. Arctic temperatures are increasing at over twice the rate of the rest of the world. Melting of glaciers and ice sheets in the Arctic disrupts ocean circulation, including a weakened Gulf Stream, further changing the climate. Section 3. Drivers of recent temperature rise. Main article, Attribution of recent climate change. There's a chart, contributors to climate change from 1850 to 1900 to the average of 2010 to 2019, as reported in the 6th IPCC Assessment Report. The IPCC found no significant contribution from internal variability or solar and volcanic drivers. The climate system experiences various cycles on its own, which can last for years, such as the El Niño Southern Oscillation, decades, or even centuries. Other changes are caused by an imbalance of energy that is external to the climate system, but not always external to the Earth. Examples of external forcings include changes in the concentrations of greenhouse gases, solar luminosity, volcanic eruptions, and variations in the Earth's orbit around the Sun. To determine the human contribution to climate change, known internal climate variability and natural external forcings need to be ruled out. A key approach is to determine unique fingerprints for all potential causes, then compare these fingerprints with observed patterns of climate change. For example, solar forcing can be ruled out as a major cause. Its fingerprint would be warming the entire atmosphere, yet only the lower atmosphere has warmed, consistent with greenhouse gas forcing. Attribution of recent climate change shows that the main driver is elevated greenhouse gases, but that aerosols also have a strong effect. Greenhouse gases. Main articles: greenhouse gas emissions, greenhouse effect, and carbon dioxide in Earth's atmosphere. The Earth absorbs sunlight, then radiates it as heat. Greenhouse gases in the atmosphere absorb and re-emit infrared radiation, slowing the rate at which it can pass through the atmosphere and escape into space. Before the Industrial Revolution, naturally occurring amounts of greenhouse gases caused the air near the surface to be about 33 degrees Celsius warmer than it would have been in their absence. While water vapour, about 50%, and clouds, about 25%, are the biggest contributors to the greenhouse effect, they increase as a function of temperature and are therefore feedbacks. On the other hand, concentrations of gases such as CO2, about 20%, tropospheric ozone, CFCs, and nitrous oxide are not temperature dependent and are therefore external forcings. Human activity since the Industrial Revolution, mainly extracting and burning fossil fuels, coal, oil, and natural gas, has increased the amount of greenhouse gases in the atmosphere, resulting in a radiative imbalance. In 2019, the concentrations of CO2 and methane had increased by about 48% and 160% respectively since 1750. These CO2 levels are higher than they have been at any time during the last 2 million years. Concentrations of methane are far higher than they were over the last 800,000 years. There's a graph. The Global Carbon Project shows how additions to CO2 since 1880 have been caused by different sources ramping up one after another. Global anthropogenic greenhouse gas emissions in 2018, excluding those from land use change, were equivalent to 52 billion tonnes of CO2. Of these emissions, 72% was CO2, 19% was methane, 6% was nitrous oxide, and 3% was fluorinated gases. CO2 emissions primarily come from burning fossil fuels to provide energy for transport, manufacturing, heating, and electricity. Additional CO2 emissions come from deforestation and industrial processes, which include the CO2 released by the chemical reactions for making cement, steel, aluminium, and fertilizer. Methane emissions come from livestock, manure, rice cultivation, landfills, wastewater, coal mining, as well as oil and gas extraction. Nitrous oxide emissions largely come from the microbial decomposition of inorganic and organic fertilizer. From a production standpoint, the primary sources of global greenhouse gas emissions are estimated as electricity and heat, 25%, agriculture and forestry, 24%, industry and manufacturing, 21%, transport, 14%, and buildings, 6%. Despite the contribution of deforestation to greenhouse gas emissions, the Earth's land surface, particularly its forests, remain a significant carbon sink for CO2. Natural processes, such as carbon fixation in the soil and photosynthesis, more than offset the greenhouse gas contributions from deforestation. The land surface sink is estimated to remove about 29% of annual global CO2 emissions. The ocean also serves as a significant carbon sink via a two-step process. First, CO2 dissolves in the surface water. Afterwards, the ocean's overturning circulation distributes it deep into the ocean's interior, where it accumulates over time as part of the carbon cycle. Over the last 2 decades, the world's oceans have absorbed 20 to 30% of emitted CO2. Aerosols and clouds. Air pollution, in the form of aerosols, not only puts a large burden on human health, but also affects the climate on a large scale. From 1961 to 1990, a gradual reduction in the amount of sunlight reaching the Earth's surface was observed, a phenomenon popularly known as global dimming, typically attributed to aerosols from biofuel and fossil fuel burning. Globally, aerosols have been declining since 1990, meaning that they no longer mask greenhouse gas warming as much. Aerosols scatter and absorb solar radiation. They also have indirect effects on the Earth's radiation budget. Sulfate aerosols act as cloud condensation nuclei and lead to clouds that have more and smaller cloud droplets. These clouds reflect solar radiation more efficiently than clouds with fewer and larger droplets. They also reduce the growth of raindrops, which makes clouds more reflective to incoming sunlight. Indirect effects of aerosols are the largest uncertainty in radiative forcing. While aerosols typically limit global warming by reflecting sunlight, black carbon in soot that falls on snow or ice can contribute to global warming. Not only does this increase the absorption of sunlight, it also increases melting and sea level rise. Limiting new black carbon deposits in the Arctic could reduce global warming by 0.2 degrees Celsius by 2050. Changes of the land surface. There's a chart. The rate of global tree cover loss has approximately doubled since 2001, to an annual loss approaching an area the size of Italy. Humans changed the Earth's surface mainly to create more agricultural land. Today, agriculture takes up 34% of Earth's land area, while 26% is forests and 30% is uninhabitable, glaciers, deserts, etc. The amount of forested land continues to decrease, largely due to conversion to cropland in the tropics. This deforestation is the most significant aspect of land surface change affecting global warming. The main causes of deforestation are permanent land use change from forest to agricultural land producing products such as beef and palm oil, 27%, logging to produce forestry or forest products, 26%, short-term shifting cultivation, 24%, and wildfires, 23%. Land use changes not only affect greenhouse gas emissions. The type of vegetation in a region affects the local temperature. It impacts how much of the sunlight gets reflected back into space, albedo, and how much heat is lost by evaporation. For instance, the change from a dark forest to grassland makes the surface lighter, causing it to reflect more sunlight. Deforestation can also affect temperatures by modifying the release of chemical compounds that influence clouds, and by changing wind patterns. In tropic and temperate areas, the net effect is to produce significant warming, while at latitudes closer to the poles, a gain of albedo, as forest is replaced by snow cover, leads to a cooling effect. Globally, these effects are estimated to have led to a slight cooling, dominated by an increase in surface albedo. Solar and volcanic activity. Further information, solar activity and climate. Physical climate models are unable to reproduce the rapid warming observed in recent decades when taking into account only variations in solar output and volcanic activity. As the sun is the Earth's primary energy source, changes in incoming sunlight directly affect the climate system. Solar irradiance has been measured directly by satellites, and indirect measurements are available from the early 1600s onwards. There has been no upward trend in the amount of the sun's energy reaching the Earth. Further evidence for greenhouse gases causing global warming comes from measurements that show a warming of the lower atmosphere, the troposphere, coupled with a cooling of the upper atmosphere, the stratosphere. If solar variations were responsible for the observed warming, the troposphere and stratosphere would both warm. Explosive volcanic eruptions represent the largest natural forcing over the industrial era. When the eruption is sufficiently strong, with sulfur dioxide reaching the stratosphere, sunlight can be partially blocked for a couple of years. The temperature signal lasts about twice as long. In the industrial era, volcanic activity has had negligible impacts on global temperature trends. Present-day volcanic CO2 emissions are equivalent to less than 1% of current anthropogenic CO2 emissions. Climate change feedback. Main articles: climate change feedback and climate sensitivity. There's an image. Sea ice reflects 50% to 70% of incoming solar radiation, while the dark ocean surface only reflects 6%, so melting sea ice is a self-reinforcing feedback. The response of the climate system to an initial forcing is modified by feedbacks, increased by self-reinforcing feedbacks, and reduced by balancing feedbacks. The main reinforcing feedbacks are the water vapor feedback, the ice albedo feedback, and probably the net effect of clouds. The primary balancing mechanism is radiative cooling, as Earth's surface gives off more heat to space in response to rising temperature. In addition to temperature feedbacks, there are feedbacks in the carbon cycle, such as the fertilizing effect of CO2 on plant growth. Uncertainty over feedbacks is the major reason why different climate models project different magnitudes of warming for a given amount of emissions. As air gets warmer, it can hold more moisture. After initial warming due to emissions of greenhouse gases, the atmosphere will hold more water. Water vapor is a potent greenhouse gas, so this further heats the atmosphere. If cloud cover increases, more sunlight will be reflected back into space, cooling the planet. If clouds become higher and thinner, they act as an insulator, reflecting heat from below back downwards and warming the planet. Overall, the net cloud feedback over the industrial era has probably exacerbated temperature rise. The reduction of snow cover and sea ice in the Arctic reduces the albedo of the Earth's surface. More of the sun's energy is now absorbed in these regions, contributing to amplification of Arctic temperature changes. Arctic amplification is also melting permafrost, which releases methane and CO2 into the atmosphere. Around half of human-caused CO2 emissions have been absorbed by land plants and by the oceans. On land, elevated CO2 and an extended growing season have stimulated plant growth. Climate change increases droughts and heat waves that inhibit plant growth, which makes it uncertain whether this carbon sink will continue to grow in the future. Soils contain large quantities of carbon, and may release some when they heat up. As more CO2 and heat are absorbed by the ocean, it acidifies, its circulation changes, and phytoplankton take up less carbon, decreasing the rate at which the ocean absorbs atmospheric carbon. Climate change can increase methane emissions from wetlands, marine and freshwater systems, and permafrost. Section 4. Future Warming and the Carbon Budget. Further information in the articles Carbon Budget, Climate Model, and Carbon Cycle. There's a pair of maps, warming distribution at 1.5 degrees Celsius, 2.7 degrees Fahrenheit average, and warming distribution at 4.0 degrees Celsius, 7.2 degrees Fahrenheit. Projected global surface temperature changes relative to 1850 to 1900 based on CMIP6 multi-model mean changes. Future warming depends on the strengths of climate feedbacks and on emissions of greenhouse gases. The former are often estimated using climate models developed by multiple scientific institutions. A climate model is a representation of the physical, chemical, and biological processes that affect the climate system. Models include changes in the Earth's orbit, historical changes in the Sun's activity, and volcanic forcing. Computer models attempt to reproduce and predict the circulation of the oceans, the annual cycle of the seasons, and the flows of carbon between the land surface and the atmosphere. Models project different future temperature rises for given emissions of greenhouse gases. They do not fully agree on the strength of different feedbacks on climate sensitivity and magnitude of inertia of the climate system. The physical realism of models is tested by examining their ability to simulate contemporary or past climates. Past models have underestimated the rate of Arctic shrinkage and underestimated the rate of precipitation increase. Sea level rise since 1990 was underestimated in older models, but more recent models agree well with observations. The 2017 United States published National Climate Assessment notes that climate models may still be underestimating or missing relevant feedback processes. A subset of climate models adds societal factors to a simple physical climate model. These models simulate how population, economic growth, and energy use affect and interact with the physical climate. With this information, these models can produce scenarios of future greenhouse gas emissions. This is then used as input for physical climate models to generate climate change projections. In some scenarios, emissions continue to rise over the century, while others have reduced emissions. Fossil fuel resources are too abundant for shortages to be relied on to limit carbon emissions in the 21st century. Emissions scenarios can be combined with modelling of the carbon cycle to predict how atmospheric concentrations of greenhouse gases might change in the future. According to these combined models, by 2100, the atmospheric concentration of CO2 could be as low as 380 or as high as 1,400 parts per million, depending on the socio-economic scenario and the mitigation scenario. The IPCC Sixth Assessment Report projects that global warming is very likely to reach 1.0 degrees Celsius to 1.8 degrees Celsius by the late 21st century under the very low GHG emissions scenario. In an intermediate scenario, global warming would reach 2.1 degrees Celsius to 3.5 degrees Celsius, and 3.3 degrees Celsius to 5.7 degrees Celsius under the very high GHG emissions scenario. These projections are based on climate models in combination with observations. The remaining carbon budget is determined by modelling the carbon cycle and the climate sensitivity to greenhouse gases. According to the IPCC, global warming can be kept below 1.5 degrees Celsius with a 2/3 chance if emissions after 2018 do not exceed 420 or 570 gigatons of CO2. This depends on how global temperature is defined. There is a small difference between air and surface temperatures. This corresponds to 10 to 13 years of current emissions. There are high uncertainties about the budget. For instance, it may be 100 gigatons of CO2 smaller due to methane release from permafrost and wetlands. Section 5. Impacts. Main article, Effects of climate change. There's a map, soil moisture change at 2.0 degrees Celsius, 3.6 degrees Fahrenheit. The 6th IPCC assessment report projects changes in average soil moisture that can disrupt agriculture and ecosystems. A reduction in soil moisture by 1 standard deviation means that average soil moisture will approximately match the 9th driest year between 1850 and 1900 at that location. Physical environment. Main article, Physical impacts of climate change. The environmental effects of climate change are broad and far-reaching, affecting oceans, ice, and weather. Changes may occur gradually or rapidly. Evidence for these effects comes from studying climate change in the past, from modelling, and from modern observations. Since the 1950s, droughts and heat waves have appeared simultaneously with increasing frequency. Extremely wet or dry events within the monsoon period have increased in India and East Asia. The rainfall rate and intensity of hurricanes and typhoons is likely increasing. Frequency of tropical cyclones has not increased as a result of climate change. There's a graph, Historical Sea Level Reconstruction and Projections up to 2100, published in 2017 by the US Global Change Research Program. Global sea level is rising as a consequence of glacial melt of the ice sheets in Greenland and Antarctica, and thermal expansion. Between 1993 and 2020, the rise increased over time, averaging 3.3 plus or minus 0.3 millimeters per year. Over the 21st century, the IPCC projects that in a very high emission scenario, the sea level could rise by 61 to 110 centimetres. Increased ocean warmth is undermining and threatening to unplug Antarctic glacier outlets, risking a large melt of the ice sheet and the possibility of a 2-metre sea level rise by 2100 under high emissions. Climate change has led to decades of shrinking and thinning of the Arctic sea ice. While ice-free summers are expected to be rare at 1.5 degrees Celsius of warming, they are set to occur once every 3 to 10 years at a warming level of 2 degrees Celsius. Higher atmospheric CO2 concentrations have led to changes in ocean chemistry. An increase in dissolved CO2 is causing oceans to acidify. In addition, oxygen levels are decreasing as oxygen is less soluble in warmer water. Dead zones in the ocean, regions with very little oxygen, are expanding too. Tipping points and long-term impacts. The greater the amount of global warming, the greater the risk of passing through tipping points, thresholds beyond which certain impacts can no longer be avoided even if temperatures are reduced. An example is the collapse of West Antarctic and Greenland ice sheets, where a temperature rise of 1.5 to 2 degrees Celsius may commit the ice sheets to melt, although the time scale of melt is uncertain and depends on future warming. Some large-scale changes could occur over a short time period, such as a collapse of the Atlantic meridional overturning circulation, which would trigger major climate changes in the North Atlantic, Europe, and North America. The long-term effects of climate change include further ice melt, ocean warming, sea level rise, and ocean acidification. On the timescale of centuries to millennia, the magnitude of climate change will be determined primarily by anthropogenic CO2 emissions. This is due to CO2's long atmospheric lifetime. Oceanic CO2 uptake is slow enough that ocean acidification will continue for hundreds to thousands of years. These emissions are estimated to have prolonged the current interglacial period by at least 100,000 years. Sea level rise will continue over many centuries, with an estimated rise of 2.3 metres per degree Celsius, 4.2 feet per degree Fahrenheit, after 2,000 years. Nature and wildlife. The main article for which is Climate Change and Ecosystems. Recent warming has driven many terrestrial and freshwater species poleward and towards higher altitudes. Higher atmospheric CO2 levels and an extended growing season have resulted in global greening. However, heat waves and drought have reduced ecosystem productivity in some regions. The future balance of these opposing effects is unclear. Climate change has contributed to the expansion of drier climate zones, such as the expansion of deserts in the subtropics. The size and speed of global warming is making abrupt changes in ecosystems more likely. Overall, it is expected that climate change will result in the extinction of many species. The oceans have heated more slowly than the land, but plants and animals in the ocean have migrated towards the colder poles faster than species on land. Just as on land, heat waves in the ocean occur more frequently due to climate change, harming a wide range of organisms such as corals, kelp, and seabirds. Ocean acidification makes it harder for organisms such as mussels, barnacles, and corals to produce shells and skeletons, and heat waves have bleached coral reefs. Harmful algal blooms enhanced by climate change and eutrophication lower oxygen levels, disrupt food webs, and cause great loss of marine life. Coastal ecosystems are under particular stress. Almost half of global wetlands have disappeared due to climate change and other human impacts. Climate change impacts on the environment. There's a series of images. Ecological collapse. Bleaching has damaged the Great Barrier Reef and threatens reefs worldwide. Extreme weather. Drought and high temperatures worsened the 2020 bushfires in Australia. Arctic warming. Permafrost thaws undermine infrastructure and release methane, a greenhouse gas. Habitat destruction. Many Arctic animals rely on sea ice, which has been disappearing in a warming Arctic. Pest propagation. Mild winters allow more pine beetles to survive to kill large swathes of forest. Humans. The main article here is Effects of Climate Change on Humans. For further information, see Effects of Climate Change on Human Health, Climate Security, Economics of Climate Change, and Climate Change and Agriculture. There's a graph. The IPCC 6th Assessment Report 2021 projects that extreme events will increase rapidly in frequency compared to the pre-industrial era. The effects of climate change on humans, mostly due to warming and shifts in precipitation, have been detected worldwide. Impacts are now observable on all continents and across ocean regions, with low-latitude, less developed areas facing the greatest risk. Continued warming has potentially severe, pervasive, and irreversible impacts for people and ecosystems. The risks are unevenly distributed, but are generally greater for disadvantaged people in developing and developed countries. Food and health. Health impacts include both the direct effects of extreme weather, leading to injury and loss of life, as well as indirect effects, such as undernutrition brought on by crop failures. Various infectious diseases are more easily transmitted in a warmer climate, such as dengue fever, which affects children most severely, and malaria. Young children are the most vulnerable to food shortages, and together with older people, to extreme heat. The World Health Organization, WHO, has estimated that between 2030 and 2050, climate change is expected to cause around 250,000 additional deaths per year from heat exposure in elderly people, increases in diarrheal disease, malaria, dengue, coastal flooding, and childhood undernutrition. Over 500,000 additional adult deaths are projected yearly by 2050 due to reductions in food availability and quality. Other major health risks associated with climate change include air and water quality. The WHO has classified human impacts from climate change as the greatest threat to global health in the 21st century. Climate change is affecting food security. It has caused reduction in global mean yields of maize, wheat, and soybeans between 1981 and 2010. Further warming could further reduce global yields of major crops. Crop production will probably be negatively affected in low-latitude countries, while effects at northern latitudes may be positive or negative. Up to an additional 183 million people worldwide, particularly those with lower incomes, are at risk of hunger as a consequence of these impacts. The effects of warming on the oceans impact fish stocks, with a global decline in the maximum catch potential. Only polar stocks are showing an increased potential. Regions dependent on glacier water, regions that are already dry, and small islands are at increased risk of water stress due to climate change. Livelihoods. Economic damages due to climate change may be severe, and there is a probability of disastrous tail risk events. Climate change has likely already increased global economic inequality, and this trend is projected to continue. Most of the severe impacts are expected in sub-Saharan Africa and Southeast Asia, where existing poverty is already exacerbated. The World Bank estimates that climate change could drive over 120 million people into poverty by 2030. Current inequalities between men and women, between rich and poor, and between different ethnicities have been observed to worsen as a consequence of climate variability and climate change. An expert elicitation concluded that the role of climate change in armed conflict has been small compared to factors such as socio-economic inequality and state capabilities, but that future warming will bring increasing risks. Low-lying islands and coastal communities are threatened through hazards posed by sea level rise, such as flooding and permanent submergence. This could lead to statelessness for populations in island nations such as the Maldives and Tuvalu. In some regions, rise in temperature and humidity may be too severe for humans to adapt to. With worst-case climate change, models project that almost one-third of humanity might live in extremely hot and uninhabitable climates, similar to the current climate found in the Sahara. These factors, plus weather extremes, can drive environmental migration, both within and between countries. Displacement of people is expected to increase as a consequence of more frequent extreme weather, sea level rise, and conflict arising from increased competition over natural resources. Climate change may also increase vulnerability, leading to trapped populations who are not able to move due to a lack of resources. Climate change impacts on people. There's a series of images. Environmental migration. Sparser rainfall leads to desertification that harms agriculture and can displace populations. Shown, Teli in Mali. Agricultural changes. Droughts, rising temperatures, and extreme weather negatively impact agriculture. Shown is Texas in the USA. Tidal flooding. Sea level rise increases flooding in low-lying coastal regions. Shown is Venice in Italy. Storm intensification. Bangladesh, after Cyclone Sidr, is an example of catastrophic flooding from increased rainfall. Heat wave intensification. Events like the June 2019 European heatwave are becoming more common. Section 6. Responses. Mitigation and adaptation. Mitigation, for which the main article is Climate Change Mitigation. There's a graph. Scenarios of global greenhouse gas emissions. If all countries achieve their current Paris Agreement pledges, average warming by 2100 would still significantly exceed the maximum 2 degrees Celsius target set by the agreement. Climate change can be mitigated by reducing greenhouse gas emissions and by enhancing sinks that absorb greenhouse gases from the atmosphere. In order to limit global warming to less than 1.5 degrees Celsius with a high likelihood of success, global greenhouse gas emissions need to be net zero by 2050, or by 2070 with a 2 degrees Celsius target. This requires far-reaching systemic changes on an unprecedented scale in energy, land, cities, transport, buildings, and industry. The United Nations Environment Programme estimates that countries need to triple their pledges under the Paris Agreement within the next decade to limit global warming to 2 degrees Celsius. An even greater level of reduction is required to meet the 1.5 degrees Celsius goal. With pledges made under the agreement as of October 2021, global warming would still have a 66% chance of reaching about 2.7 degrees Celsius, the range is 2.2 to 3.2 degrees Celsius, by the end of the century. Although there is no single pathway to limit global warming to 1.5 or 2 degrees Celsius, most scenarios and strategies see a major increase in the use of renewable energy in combination with increased energy efficiency measures to generate the needed greenhouse gas reductions. To reduce pressures on ecosystems and enhance their carbon sequestration capabilities, changes would also be necessary in agriculture and forestry, such as restoring natural ecosystems by reforestation. Other approaches to mitigating climate change have a higher level of risk. Scenarios that limit global warming to 1.5 degrees Celsius typically project the large-scale use of carbon dioxide removal methods over the 21st century. There are concerns, though, about over-reliance on these technologies, as well as environmental impacts. Solar radiation management, SRM, is also a possible supplement to deep reductions in emissions. However, SRM would raise significant ethical and legal issues, and the risks are poorly understood. Clean energy, for which the main articles are sustainable energy and sustainable transport. There's a chart. Global energy consumption 2000 to 2019. Coal, oil and natural gas remain the primary global energy sources, even as renewables have begun rapidly increasing. There's another chart. Economic sectors with more greenhouse gas contributions have a greater stake in climate change policies. Renewable energy is key to limiting climate change. Fossil fuels accounted for 80% of the world's energy in 2018. The remaining share was split between nuclear power and renewables, including solar and wind power, bioenergy, geothermal energy, and hydropower. That mix is projected to change significantly over the next 30 years. Solar and wind have seen substantial growth and progress over the last few years. Solar panels and onshore wind are the cheapest forms of adding new power generation capacity in most countries. Renewables represented 75% of all new electricity generation installed in 2019, nearly all solar and wind. Meanwhile, nuclear power share remains the same, but costs are increasing. Nuclear power generation is now several times more expensive per megawatt hour than wind and solar. To achieve carbon neutrality by 2050, renewable energy would become the dominant form of electricity generation, rising to 85% or more by 2050 in some scenarios. The use of electricity for heating and transport would rise to the point where electricity becomes the largest form of energy. Investment in coal would be eliminated and coal use nearly phased out by 2050. In transport, scenarios envision sharp increases in the market share of electric vehicles, and a switch to low-carbon fuel for other transportation modes like shipping. Heating would be increasingly decarbonised with the use of technologies like heat pumps. There are obstacles to the continued rapid growth of renewables. For solar and wind power, a key challenge is their intermittency and seasonal variability. Traditionally, hydro dams with reservoirs and conventional power plants have been used when variable energy production is low. Intermittency is further countered by expanding battery storage and matching energy demand and supply. Long-distance transmission can smooth variability of renewable output across wider geographic areas. There can be environmental and land use concerns with large solar and wind projects, while bioenergy is often not carbon neutral and may have negative consequences for food security. Hydropower growth has been slowing and is set to decline further due to concerns about social and environmental impacts. Low-carbon energy improves human health by minimising climate change and has the near-term benefit of reducing air pollution deaths, which were estimated at 7 million annually in 2016. Meeting the Paris Agreement goals that limits warming to a 2-degree increase could save about 1 million of those lives per year by 2050, whereas limiting global warming to 1.5 degrees Celsius could save millions and simultaneously increase energy security and reduce poverty. Energy efficiency. See also efficient energy use. Reducing energy demand is another major aspect of reducing emissions. If less energy is needed, there is more flexibility for clean energy development. It also makes it easier to manage the electricity grid and minimises carbon-intensive infrastructure development. Major increases in energy efficiency investment will be required to achieve climate goals, comparable to the level of investment in renewable energy. Several COVID-19 related changes in energy use patterns, energy efficiency investments, and funding have made forecasts for this decade more difficult and uncertain. Strategies to reduce energy demand vary by sector. In transport, passengers and freight can switch to more efficient travel modes such as buses and trains, or use electric vehicles. Industrial strategies to reduce energy demand include increasing the energy efficiency of heating systems and motors, designing less energy-intensive products, and increasing product lifetimes. In the building sector, the focus is on better design of new buildings and aiming for higher levels of energy efficiency in retrofitting. The use of technologies like heat pumps can also increase building energy efficiency. Agriculture and industry. See also sustainable agriculture and green industrial policy. Agriculture and forestry face a triple challenge of limiting greenhouse gas emissions, preventing the further conversion of forests to agricultural land, and meeting increases in world food demand. A set of actions could reduce agriculture and forestry-based emissions by 2/3 from 2010 levels. These include reducing growth in demand for food and other agricultural products, increasing land productivity, protecting and restoring forests, and reducing greenhouse gas emissions from agricultural production. Steel and cement production, responsible for about 13% of industrial CO2 emissions, present particular challenges. In these industries, carbon-intensive materials such as coke and lime play an integral role in their production, so that reducing CO2 emissions requires research into alternative chemistries. Carbon sequestration. Main articles: carbon capture and storage, carbon dioxide removal, and carbon sequestration. There's a graph: carbon dioxide partitioning. Most CO2 emissions have been absorbed by carbon sinks, including plant growth, soil uptake, and ocean uptake. 2020 Global Carbon Budget. Natural carbon sinks can be enhanced to sequester significantly larger amounts of CO2 beyond naturally occurring levels. Reforestation and tree planting on non-forest lands are among the most mature sequestration techniques, although the latter raises food security concerns. Soil carbon sequestration and coastal carbon sequestration are less understood options. The feasibility of land-based negative emissions methods for mitigation are uncertain. The IPCC has described mitigation strategies based on them as risky. Where energy production or CO2-intensive heavy industries continue to produce waste CO2, the gas can be captured and stored instead of released to the atmosphere. Although its current use is limited in scale and expensive, carbon capture and storage, CCS, may be able to play a significant role in limiting CO2 emissions by mid-century. This technique, in combination with bioenergy, BECCS, can result in net negative emissions. CO2 is drawn from the atmosphere. It remains highly uncertain whether carbon dioxide removal techniques, such as BECCS, will be able to play a large role in limiting warming to 1.5 degrees Celsius. Policy decisions that rely on carbon dioxide removal increase the risk of global warming rising beyond international goals. Adaptation, for which the main article is Climate Change Adaptation. Adaptation is the process of adjustment to current or expected changes in climate and its effects. Without additional mitigation, adaptation cannot avert the risk of severe, widespread, and irreversible impacts. More severe climate change requires more transformative adaptation, which can be prohibitively expensive. The capacity and potential for humans to adapt is unevenly distributed across different regions and populations, and developing countries generally have less. The first 2 decades of the 21st century saw an increase in adaptive capacity in most low and middle income countries with improved access to basic sanitation and electricity, but progress is slow. Many countries have implemented adaptation policies. However, there is a considerable gap between necessary and available finance. Adaptation to sea level rise consists of avoiding at-risk areas, learning to live with increased flooding, and protection. If that fails, managed retreat may be needed. There are economic barriers for tackling dangerous heat impact. Avoiding strenuous work or having air conditioning is not possible for everybody. In agriculture, adaptation options include a switch to more sustainable diets, diversification, erosion control, and genetic improvements for increased tolerance to a changing climate. Insurance allows for risk sharing, but is often difficult to get for people on lower incomes. Education, migration, and early warning systems can reduce climate vulnerability. Ecosystems adapt to climate change, a process that can be supported by human intervention. By increasing connectivity between ecosystems, species can migrate to more favourable climate conditions. Species can be directly moved as well. Protection and restoration of natural and semi-natural areas helps build resilience, making it easier for ecosystems to adapt. Many of the actions that promote adaptation in ecosystems also help humans adapt via ecosystem-based adaptation. For instance, restoration of natural fire regimes makes catastrophic fires less likely and reduces human exposure. Giving rivers more space allows for more water storage in the natural system, reducing flood risk. Restored forest acts as a carbon sink, but planting trees in unsuitable regions can exacerbate climate impacts. There are synergies and trade-offs between adaptation and mitigation. Adaptation often offers short-term benefits, whereas mitigation has longer-term benefits. Increased use of air conditioning allows people to better cope with heat, but increases energy demand. Compact urban development may lead to reduced emissions from transport and construction. At the same time, it may increase the urban heat island effect, leading to higher temperatures and increased exposure. Increased food productivity has large benefits for both adaptation and mitigation. Section 7. Policies and Politics. The main article is Politics of Climate Change. There's a map. The Climate Change Performance Index ranks countries by greenhouse gas emissions, 40% of score, renewable energy, 20%, energy use, 20%, and climate policy, 20%. Countries that are most vulnerable to climate change have typically been responsible for a small share of global emissions. This raises questions about justice and fairness. Climate change is strongly linked to sustainable development. Limiting global warming makes it easier to achieve sustainable development goals, such as eradicating poverty and reducing inequalities. The connection is recognised in Sustainable Development Goal 13, which is to take urgent action to combat climate change and its impacts. The goals on food, clean water, and ecosystem protection have synergies with climate mitigation. The geopolitics of climate change is complex. It has often been framed as a free rider problem, in which all countries benefit from mitigation done by other countries, but individual countries would lose from switching to a low-carbon economy themselves. This framing has been challenged. For instance, the benefits of a coal phase-out to public health and local environments exceed the costs in almost all regions. Furthermore, net importers of fossil fuels win economically from switching to clean energy, causing net exporters to face stranded assets, fossil fuels they cannot sell. Policy options. A wide range of policies, regulations and laws are being used to reduce emissions. As of 2019, carbon pricing covers about 20% of global greenhouse gas emissions. Carbon can be priced with carbon taxes and emissions trading systems. Direct global fossil fuel subsidies reached $319 billion in 2017, and $5.2 trillion when indirect costs such as air pollution are priced in. Ending these can cause a 28% reduction in global carbon emissions and a 46% reduction in air pollution deaths. Subsidies could be used to support the transition to clean energy instead. More direct methods to reduce greenhouse gases include vehicle efficiency standards, renewable fuel standards, and air pollution regulations on heavy industry. Several countries require utilities to increase the share of renewables in power production. Policy designed through the lens of climate justice tries to address human rights issues and social inequality. Wealthy nations responsible for the largest share of emissions would have to pay poorer countries to adapt. As the use of fossil fuels is reduced, jobs in the sector are being lost. To achieve a just transition, these people would need to be retrained for other jobs. Communities with many fossil fuel workers would need additional investments. International climate agreements. Further information at United Nations Framework Convention on Climate Change. There are two graphs. Since 2000, rising CO2 emissions in China and the rest of the world have surpassed the output of the United States and Europe. And, per person, the United States generates CO2 at a far faster rate than other primary regions. Nearly all countries in the world are parties to the 1994 United Nations Framework Convention on Climate Change, UNFCCC. The goal of the UNFCCC is to prevent dangerous human interference with the climate system. As stated in the Convention, this requires that greenhouse gas concentrations are stabilized in the atmosphere at a level where ecosystems can adapt naturally to climate change, food production is not threatened, and economic development can be sustained. The UNFCCC does not itself restrict emissions, but rather provides a global framework for protocols that do. Global emissions have risen since the UNFCCC was signed. Its yearly conferences are the stage of global negotiations. The 1997 Kyoto Protocol extended the UNFCCC and included legally binding commitments for most developed countries to limit their emissions. During the negotiations, the G77, representing developing countries, pushed for a mandate requiring developed countries to take the lead in reducing their emissions, since developed countries contributed most to the accumulation of greenhouse gases in the atmosphere. Per capita emissions were also still relatively low in developing countries, and developing countries would need to emit more to meet their development needs. The 2009 Copenhagen Accord has been widely portrayed as disappointing because of its low goals, and was rejected by poorer nations including the G77. Associated parties aimed to limit the global temperature rise to below 2 degrees Celsius. The accord set the goal of sending $100 billion per year to developing countries for mitigation and adaptation by 2020, and proposed the founding of the Green Climate Fund. As of 2020, the fund has failed to reach its expected target, and risks a shrinkage in its funding. In 2015, all UN countries negotiated the Paris Agreement, which aims to keep global warming well below 2 degrees Celsius, and contains an aspirational goal of keeping warming under 1.5 degrees Celsius. The agreement replaced the Kyoto Protocol. Unlike Kyoto, no binding emission targets were set in the Paris Agreement. Instead, a set of procedures was made binding. Countries have to regularly set ever more ambitious goals and re-evaluate these goals every 5 years. The Paris Agreement restated that developing countries must be financially supported. As of October 2021, 194 states and the European Union have signed the treaty, and 191 states and the EU have ratified or acceded to the agreement. The 1987 Montreal Protocol, an international agreement to stop emitting ozone-depleting gases, may have been more effective at curbing greenhouse gas emissions than the Kyoto Protocol specifically designed to do so. The 2016 Kigali Amendment to the Montreal Protocol aims to reduce the emission of hydrofluorocarbons, a group of powerful greenhouse gases which served as a replacement for banned ozone-depleting gases. This made the Montreal Protocol a stronger agreement against climate change. National responses. In 2019, the United Kingdom Parliament became the first national government to declare a climate emergency. Other countries and jurisdictions followed suit. That same year, the European Parliament declared a climate and environmental emergency. The European Commission presented its European Green Deal with the goal of making the EU carbon neutral by 2050. Major countries in Asia have made similar pledges. South Korea and Japan have committed to become carbon neutral by 2050 and China by 2060. In 2021, the European Commission released its Fit for 55 legislation package, which contains guidelines for the car industry. All new cars on the European market must be zero-emission vehicles from 2035. While India has strong incentives for renewables, it also plans a significant expansion of coal in the country. As of 2021, based on information from 48 national climate plans, which represent 40% of the parties to the Paris Agreement, estimated total greenhouse gas emissions will be 0.5% lower compared to 2010 levels, below the 45 or 25% reduction goals to limit global warming to 1.5 degrees Celsius or 2 degrees Celsius respectively. Section 8. Scientific Consensus and Society. Scientific Consensus. The main article is Scientific Consensus on Climate Change. There's a chart. Academic studies of scientific agreement on human-caused global warming among climate experts, 2010 to 2019, reflect that the level of consensus correlates with expertise in climate science. There is a near complete scientific consensus that the climate is warming and this is caused by human activities. Agreement in recent literature reached over 99%. Older surveys found 90% to 100% of climate scientists agreeing on humanity's role in causing climate change, based on the exact question and who responded. No scientific body of national or international standing disagrees with this view. Consensus has further developed that some form of action should be taken to protect people against the impacts of climate change. National science academies have called on world leaders to cut global emissions. Scientific discussion takes place in journal articles that are peer-reviewed. Scientists assess these every few years in the Intergovernmental Panel on Climate Change Reports. The 2021 IPCC assessment report stated that it is unequivocal that climate change is caused by people. Public awareness. Further information in the articles Climate Communication, Media Coverage of Climate Change, and Public Opinion on Climate Change. Climate change came to international public attention in the late 1980s. Due to confusing media coverage in the early 1990s, people often confounded climate change with other environmental issues like ozone depletion. In popular culture, the first movie to reach a mass public on the topic was The Day After Tomorrow in 2004, followed a few years later by the Al Gore documentary An Inconvenient Truth. Books, stories, and films about climate change fall under the genre of climate fiction. Significant regional, gender, age, and political differences exist in both public concern for and understanding of climate change. More highly educated people, and in some countries, women and younger people, were more likely to see climate change as a serious threat. Partisan gaps also exist in many countries, and countries with high CO2 emissions tend to be less concerned. Views on causes of climate change vary widely between countries. Concern has increased over time to the point where a majority of citizens in many countries now express a high level of worry about climate change or view it as a global emergency. Higher levels of worry are associated with stronger public support for policies that address climate change. Denial and misinformation. Further information in the Fossil Fuels Lobby, Climate Change Denial, and Global Warming Conspiracy Theory articles. There's an image. Data has been cherry-picked from short periods to falsely assert that global temperatures are not rising. Blue trend lines show short periods that mask longer-term warming trends, red trend lines. Blue dots show the so-called global warming hiatus. Public debate about climate change has been strongly affected by climate change denial and misinformation, which originated in the United States and has since spread to other countries, particularly Canada and Australia. The actors behind climate change denial form a well-funded and relatively coordinated coalition of fossil fuel companies, industry groups, conservative think tanks, and contrarian scientists. Like the tobacco industry before, the main strategy of these groups has been to manufacture doubt about scientific data and results. Many who deny, dismiss, or hold unwarranted doubt about the scientific consensus on anthropogenic climate change are labelled as climate change skeptics, which several scientists have noted is a misnomer. There are different variants of climate denial. Some deny that warming takes place at all, some acknowledge warming but attribute it to natural influences, and some minimise the negative impacts of climate change. Manufacturing uncertainty about the science later developed into a manufactured controversy, creating the belief that there is significant uncertainty about climate change within the scientific community in order to delay policy changes. Strategies to promote these ideas include criticism of scientific institutions and questioning the motives of individual scientists. An echo chamber of climate-denying blogs and media has further fermented misunderstanding of climate change. Protests and lawsuits. Main articles: climate movement and climate change litigation. There's an image: Canadian residents protesting against global warming. Climate protests have risen in popularity in the 2010s. These protests demand that political leaders take action to prevent climate change. They can take the form of public demonstrations, fossil fuel divestment, lawsuits, and other activities. Prominent demonstrations include the School Strike for Climate. In this initiative, young people across the globe have been protesting since 2018 by skipping school on Fridays, inspired by Swedish teenager Greta Thunberg. Mass civil disobedience actions by groups like Extinction Rebellion have protested by disrupting roads and public transport. Litigation is increasingly used as a tool to strengthen climate action from public institutions and companies. Activists also initiate lawsuits which target governments and demand that they take ambitious action or enforce existing laws on climate change. Lawsuits against fossil fuel companies generally seek compensation for loss and damage. Section 9. Discovery. For broader coverage of this topic, see History of Climate Change Science. There's an image: Tyndall's ratiospectrophotometer, drawing from 1861, measured how much infrared radiation was absorbed and emitted by various gases filling its central tube. In the 1820s, Joseph Fourier proposed the greenhouse effect to explain why Earth's temperature was higher than the sun's energy alone could explain. Earth's atmosphere is transparent to sunlight, so sunlight reaches the surface where it is converted to heat. However, the atmosphere is not transparent to heat radiating from the surface, and captures some of that heat which warms the planet. In 1856, Eunice Newton Foote demonstrated that the warming effect of the sun is greater for air with water vapour than for dry air, and the effect is even greater with carbon dioxide. She concluded that an atmosphere of that gas would give to our Earth a high temperature. Starting in 1859, John Tyndall established that nitrogen and oxygen, together totaling 99% of dry air, are transparent to radiated heat. However, water vapour and some gases, in particular methane and carbon dioxide, absorb radiated heat and re-radiate that heat within the atmosphere. Tyndall proposed that changes in the concentrations of these gases may have caused climatic changes in the past, including ice ages. Svante Arrhenius noted that water vapour in air continuously varied, but the CO2 concentration in air was influenced by long-term geological processes. At the end of an ice age, warming from increased CO2 levels would increase the amount of water vapour, amplifying warming in a feedback loop. In 1896, he published the first climate model of its kind, showing that halving of CO2 levels could have produced the drop in temperature initiating the ice age. Arrhenius calculated the temperature increase expected from doubling CO2 to be around 5 to 6 degrees Celsius. Other scientists were initially skeptical and believed the greenhouse effect to be saturated, so that adding more CO2 would make no difference. They thought climate would be self-regulating. From 1938 onwards, Guy Stewart Callendar published evidence that climate was warming and CO2 levels rising, but his calculations met the same objections. In the 1950s, Gilbert Plass created a detailed computer model that included different atmospheric layers and the infrared spectrum. This model predicted that increasing CO2 levels would cause warming. Around the same time, Hans Suess found evidence that CO2 levels had been rising, and Roger Revelle showed that the oceans would not absorb the increase. The two scientists subsequently helped Charles Keeling to begin a record of continued increase, which has been termed the Keeling curve. Scientists alerted the public, and the dangers were highlighted at James Hansen's 1988 congressional testimony. The Intergovernmental Panel on Climate Change, set up in 1988 to provide formal advice to the world's governments, spurred interdisciplinary research. This sound file and all text in the article are licensed under the Creative Commons Attribution Share-alike 3.0 Unported License, available at creativecommons.org/licenses/by-sa/3.0.